Hello, Miss Wade. This is my function. I hope you're having a fantastic day. And I actually completely dumped my old function, and let's get into this new one, which is quite fun. So let me first set up the asymptote. So we have two asymptotes. One's vertical, which is x equals -1, meaning that x has no real values, and the function is undefined at x equals -1. And we also have an oblique asymptote in this case, and it's actually because our function is top heavy, meaning our numerator has a higher exponent than our denominator. Okay, so the way we calculate that was just to use limit test we can, and then use long division of dividing the numerator by the denominator, which gives you the quotient, and that's the equation of the line right here. And that makes sense because that's our oblique asymptote. Well, our asymptotes, with that being said, it doesn't have a crossover points, meaning our actual function never touches the asymptotes. So that's quite unfortunate. Um, yeah, so the other thing was the domain. So let's actually take a look at the points right here, the x-intercept. So I have these 2 points. Well, you think there are two x-intercepts, but indeed there's only one. So y-intercept is right here, 0, 0. X-intercept is only at 0, 0. Here's why. So when you factor out the x-intercepts, you cross out x minus 1 on both the numerator and the denominator. So you can't just leave it like that. You have to set up a restriction of x cannot equals to 1, because when you plug in 1 into the function, it causes the denominator to be a 0, which causes the function to be undefined because there's no real value at x equals to 1. So with that being said, theoretically it should have two zeros, but because due to our restriction of x cannot equals to 1, we only have 1 0, and it's only 0, 0. Okay, now let's talk about our first and second derivatives. All right, let's jump into the first derivative as shown through green. Mine completely matches with the one from decimal. So this is mine. This is the decimal one. So what the first derivative tells us is that tells us if the function has an increasing interval or decreasing interval. So from here, whenever our first derivative touches the x-axis, which causes the 0, or x-intercepts, it means there is a turning point on our original function, which quite makes sense. Because if you take a look at here, boom, turning point, and we call this a local minimum, and we call this a local maximum. Okay, so the way we find intervals of increase and decrease was to sub in whatever value from the left side of our local minimum, and it's this is called the decreasing interval, and then from here we'll have increasing interval, and then here a lot of people mess up because they think this is decrease, but you read graph from left to right. So this is actually increasing from our vertical asymptote to our local maximum. And then we have another decreasing intervals from our local maximum to positive infinity. Okay, so with that being said, let me actually set up so that we are ready for our second derivative. So what does second derivative do? It actually means a lot. It actually says a lot about our original function. So whenever our second derivative is above the x-axis, meaning that y is greater than 0, it means our original function is concaving up, which kind of makes sense because right here, our second derivative is above the x-axis and our original function is concaving up. And then over here, our second derivative is below the x-axis. Um, and our original function over here is also concaving down. So, yeah, with that being said, that's it for my my function, and I hope you enjoyed it. Thank you, Miss Wade. Hope you have a great day. Let me just actually pull out all the points so you can take a final look. All right, thank you.